Start recording. Hi, welcome to our second meeting. So, yeah. First we have a recap from our last meeting, and go to the next slide. Last time we looked at light as a wave, and specifically we looked at this double slit experiment, and from it we have discovered some interesting properties of light, and we discovered that it's it's a wave. So the experiment proves it by showing that first of all it has diffraction patterns. So if you see if light is a particle, it is unlikely to bends around the corner and spread out as these wavefronts. So the double slit experiment proves that light acts as wave, and when their crests meet in the middle, you will see the red parts light constructs, and it also has wavelength, frequency, and wave speed, and all the properties of wave. We see that on the wall, if we use sunlight instead of monochromatic light, different wavelengths will have different patterns presented on the wall. Yeah.
So this principle was built on by Faraday and Maxwell in electromagnetism. So on the right, you can see this GIF, this animation. So what we're seeing here is that we have an electric field, right? And that's kind of going up and down in the Y direction. And you have a magnetic field that's going back and forth in the Z direction. And you can see that the whole wave, overall, it's propagating in the X direction. So today we'll look at some other interesting properties of light. And there's also wave-particle duality, which we'll look at later. And so in terms of the news, we have this first photograph from 2015 of light as both a wave and a particle. And it's from the researchers at EPFL. And today we're going to look a little bit more at their clever trick and how they were able to capture this photo. We're going to watch a short video regarding that. About 2 minutes long.
Rohan, you have to unmute or else we can't hear anything.
Electrons want to hit them, and I slow down this change in speed, and the measured as an exchange of energy packets between the particles. So far, several experiments have confirmed that light is indeed the problem is that in such experiments, light behaves as a wave, and a telephone wave is both at the same time.
Okay, so there are some problems hearing the video. So I'll give you guys 2 minutes to go ahead and watch the video. I think Alan posted that link in the chat. I'll repost that. There's the link. So just go ahead and watch that link for 2 minutes, and in 2 minutes, I'll quickly check back. All right, so seeing that 2 minutes have passed, we will continue. This is a quick slide about atomic spectra, a property of light. So here you have a power plant. Is my mouse cursor visible? I think it is visible. So here's the power plant. You can see on the top left, and that's connected to hydrogen gas. Hydrogen gas gets excited, and that creates light. And what happens here is that we use a Newtonian trick. We take this prism, right? And we have light on that prism, and it's reflected so that we can observe the nature of light here. And so here, we can see that there's the different intensities of light, right? And there's these discrete sort of packets of light. That idea is introduced. You can see light at various intensities. These are in angstroms. You can see at the bottom right, it's measured in angstroms, which is about 10 to the minus 10th meters, a little smaller than a nanometer. So here you can see that there are these different intensities of light that we get from these excited hydrogen atoms. And if we change the power plant, that doesn't make much of a difference in the experiment. And there's so a lot of experimental factors don't make a difference. And even if we change like the gas, there's always going to be like an algebraic equation that kind of nails these lines every time. So we see this theme here that light can be discrete and structured, and that the atomic spectra can be discrete and structured. We can see these different packets of light. So just an idea to keep in the back of your minds today.
We can talk about this like in later introduction of the quantum physics, because it kind of interfere with a property called wave particle duality, which we are going to mention today. So before I was going to deep into an interesting phenomenon called photoelectron effect, I'm going to talk about blackbody radiation. So blackbody radiation is in a speech of 1900, Lord Kelvin, he describes a phenomenon called he described that there are two dark clouds that is on the top of classical physics. Because at that time, classical physics have this idea that they can solve literally everything. So all the thing about all dynamics problems can be solved by force, velocity, acceleration, or thermodynamic problem can be solved by the law of thermodynamics, or all the electromagnetic can be solved by the Maxwell's equation, and everything is just like there are no future in physics. They think that the physics is actually dead, but now they observe something that feels different from what from the classical physics viewpoint. So before I talk about this experiment, I'm going to describe this phenomenon called blackbody radiation. So what is a blackbody? Blackbody is a matter that also absorbs all kinds of electromagnetic radiation. So basically, in every spectrum, this thing is completely black. It can absorb literally everything, but it doesn't mean that it will not give out radiation, but it just eat every radiation that come onto him. So the blackbody radiation is the emission of the electromagnetic radiation from blackbody. So basically he eat in, but then he spits out something. In real life, perfect blackbody does not exist, but its radiation can be approximated through some objects that are similar, like for example, a small hole that is in a hollow body. You can shoot light into the body and test the radiation come out of it. So here is a small graph of its radiation versus the wavelength. Next slide, please. Okay, so it's known that physicists likes to give equation to everything. So they try to make an equation of the blackbody radiation. So usually people consider the radiation as a wave. So they use this to create two equations. First one is Wien's equation. So the Wien's equation is not really based on any like idea. They are just trying to suit the experiment. So he does not use like the idea that electromagnetic wave is a wave. He just like tries to get it, but he finds out that when the frequency is low, then it becomes inaccurate. So on the right graph, the green graph is the accurate description, and the blue is the Wien's equation. So another two people, Rayleigh and Jeans, they create a Rayleigh-Jeans equation that tries to describe this phenomenon. This one is fully based on like conceptual, like the idea that electromagnetic radiation is a wave. But they made the same mistakes. They made a different mistake. It's just the opposite. Like when the frequency is low, it perfectly matches the graph. But when the frequency is high, it just comes to the infinity. This is known as the ultraviolet catastrophe, which we'll talk about later. But Planck's law, however, it matches the experiment result completely, which is that green line on the graph. Wrong slide. So just a quick poll. What do you think that blackbody? What is the blackbody? And which law best describes the blackbody radiation?
Please put your answers in the chat.
All right, let's continue.
And we should quickly review the quick poll. For the black body can absorb or radiate. And for the blackbody radiation, we can describe it using Planck's law, is the main point here, 2b. And
so let's look at Planck's law. So at the top, at the right top is Planck's law, and the right bottom is Wien's law. If you really put it, you can find that the only difference between these two laws is that Planck put a -1, and which it can be hypothesized that he does not derive this law first. He just made some small adjustment and just happened to find that this matches in the experiment. So what Planck later did. So Planck get this equation, but he does not know like how did this thing came from. So he have to get an answer for it. So he just assumed so his idea at that time is hard to understand because he does not actually believe that wave is a particle. So he made a small assumption that the energy of charged particles in the magnetic field is some multiple of basic energy level, which will be later known as quantum. So it brings him like, it really makes him like the first one who actually discovers uses the idea of quantum physics. So there are two misbeliefs. So the first one is Planck quantized the electromagnetic waves. So although he gives out the equation, he does not really believe that it can be quantized. He just like uses the equation in his favor. The second one, the Planck's motivation is to solve the ultraviolet catastrophe. So as I've said, the ultraviolet catastrophe is an incident which, according to the calculation of classical physics, so the frequency of radiation goes, when the frequency of radiation, it goes over ultraviolet frequency, the energy of radiation just goes to infinity. So but Planck come up with the radiation law like before the ultraviolet catastrophe happens. So its application in astronomy is that the star can be considered as objects that are really similar to black bodies. So Planck law can help scientists determine stars' temperature and also using their light. So it's a bit helpful on that perspective.
Yeah, and also notice there's no perfect black body, so in real life the curve won't be as smooth. Like sun, there was a picture that we showed before. It actually has something that's a characterization of a specific star in astronomy.
All right, here we have another quick poll. Just post A, B, or C in the chat. Which law incorporates the idea of quantum in its calculation of radiance density? All right. So because of time, I'll quickly go over it. So here it's because of Planck's law, which we mentioned earlier, how Planck established some basic quantum ideas through the blackbody radiation. And so here we have the photoelectric effect. And so this relates a lot to the atomic spectra and then blackbody radiation. All of it's kind of leading up to the photoelectric effect, where a lot of this quantum stuff demands an explanation. And so on photoelectric effect, right here we can see the charged particles are released from a material when it absorbs the electromagnetic radiation, which is just like the light wave, right? And so light is going to hit the object you can see in the photo bottom right, and then the electrical charged particles are released. The electrons are released, and the energy of the charged particles is determined by the frequency of the light and not the amplitude. And so here you can see the idea of the photoelectric effect we can see in this picture right here, where you have the sunlight, and you can see this positively charged plate, right? And the electrons are going to fly off this plate to the negatively charged plate. And so you're inducing an electric potential, right? Because there's a negatively charged plate over here, There's a positively charged plate over here. The electrons are flying off. And so we have the ammeter right here, the voltmeter should, which is labeled with I, should detect a voltage, or a current, sorry. And so this effect was observed by Heinrich Hertz, but it could not be explained with wave theory. And the wave theory considered the energy of light related to the amplitude, which is correct.
Carry on, but I'm out of here.
Do we have to close the meeting?
You guys can continue, but I have to leave the building.
All right. So if we introduce a voltage source, so imagine, I don't know, can we annotate on the slides? I think we can. No, we can't. All right. So is that visible?
You need to go back to slide 9 because it's a small mess up.
Small mistake on slide 9. All right. Let's go back to slide 9. Is this slide?
No, it's not one about photon. Oh, it's not. No.
Which slide? This slide. Oh, this slide has been. It was like redirected, right? Was this supposed to come like here or?
Yeah. Let's read this.
All right. So here we have the slide about photons. So in 1905, Einstein published his hypothesis that light is made of packets, right? It's made of quanta. We observed before through the atomic spectra, right? So light is made of quanta called photons. They're these packets of light. And this is determined by Planck's equation, where we have E equals hf, where h is Planck's constant and f is frequency, right? Planck's constant is determining the spacing of those packets of light. And so the amplitude of light is the intensity of the photon here. And you can see this picture. I'm depicting that. So we were making a few last minute changes to the slide, so the ordering got a little bit messed up. So we're over here, and so we had the photoelectric effect. And so if we draw like a voltage source, I know that was a bad annotation, but here we have a voltage source, and that introduces the electric potential difference, right? And so reducing the voltage magnitude will make it easier for the electrons to cross from the positive plate to the negative plate, right? And if we increase the voltage magnitude, that makes it more difficult for the electrons to cross. And increasing light intensity will make it also easier for the electrons to get across. And so by analyzing the amount of the voltage and the current and the intensity, we can reach the E equals HV conclusion, E equals HF.
So here is the proof of Einstein's idea of photoelectron. Electric effect. Since Einstein's idea, it perfectly like explain it, but it does need some experiment proof. So in 1960, Robert Millikan does an experiment. He tries to prove that Einstein explanation, whether it matches the phenomenon and or not. But later he actually proves it. So in the way he proves it is really simple. So look at the graph on the right. So its x-axis is frequency, its y-axis is like photoelectron kinetic energy, is just E. So as long as they form a straight line that with a slope of h, which is the Planck constant, you can actually say that his idea is just correct. And both of them won the Nobel Physics Prize. A fun fact is that Millikan's initial motivation is to prove that Einstein is wrong because he is a believer of wave theory of light, but later he not only prove it is correct, and he also get Nobel Prize for it. I don't know how does he feel. An application. So the devices made by photoelectric have several desirable properties, which are ability to detect small amount of light and a fast response time. Some examples can be night vision device. So it's a kind of night vision device. They takes in like small amount of light and then magnifies its light source. The next one is photo multiplier, which detects small amount of light, and photoelectron spectroscopy, which is used to determine the binding energy of electrons.
So here we quickly have wave versus particle. This is the last slide. We're almost out of time. And so we see that the particle, you can read the slide here, and its particle in Newton's terms, it has zero size and it just carries energy and it has position and velocity. But later on, we're going to introduce these quantum mechanical ideas, right? Where a particle is just some indivisible amount of energy or momentum that propagates, right? We have a loss of determinism. And so quantum mechanical particle is just a packet of energy that is indivisible, right? And we have photons, which is a quantum mechanical particle, packet of energy. So next time we'll do like a brief recap. There's like a conclusion on this slide. But time is up. I think, Alan, if we could like switch to view mode and then share these slides.
Yeah, and also please fill out the survey in the chat. The feedback you guys gave us last time was very helpful, and this time the survey is a bit shorter, so hopefully you guys can fill it out before you leave. And I'll send a slide in the chat if you guys want to revisit it.
And quick shout out to Alex for all of his hard work, because he's been doing like a lot of hard work on the slides and the lectures throughout the past week. So he worked really hard on this week's slides and helped us out a lot this week. So thank you to Alex.
Thank you. All right, you guys are free to leave.
Good job, Alex.
Thank you.
Thank you.
We can email out the slides then.
Sure.
Hey, Alan, is there a place on V Clubs to post all the slides in the video?
We can post videos. We can put a link to our slides.
Okay.
Yeah.
Nice. Yeah, nice job.
Thank you.
I think if you want to do polls again in the future, I think Zoom has an actual poll feature, but I'm not sure where it is or how it works really. But it exists, so yeah. Let me look it up.
I think under co-host we have like the polls option. I see like the physics C poll right here. Would you like to
I think the Google Forms is actually a better way to poll.
It will be better if you guys send the form to them before, like after they leave, because if they did not get it through the chat, then they can access it through the Gmail.
Okay, I see 7 people responded, so to the Google form.
We have 7 responses.
Yeah.
What are people saying generally about the difficulty for today, or like how interesting it was?
It's really good. It's so difficulty level is 6 3s and 1 4. And interesting level is 2 3, 2 4, and 3 5s.
All right, well, that's an improvement.
Yeah.
All right, nice job, everyone. Good work today.
Yeah. Have a great day.
Thank you. Bye.
Thanks, Alex.
Thank you, Alex.
Thank you, everyone.
Thank you.
Bye, Jen.